Hello everyone, welcome to today's live broadcast, Tracking VOCs and their life cycles in the atmosphere with modern spectroscopic technologies. I'm Kate Mossford, Managing Editor, and I'll be your moderator for today's event. We are pleased to bring you this web seminar presented by Spectroscopy and sponsored by Princeton Instruments. Princeton Instruments provides state-of-the-art CCD, SCMOS, ICCD, EMCCD, EMICCD, X-ray and InGas cameras, spectrometers, spectrographs, imaging systems, optics and coatings that are key to the success of your application. We take pride in partnering with our customers to solve their most challenging problems in unique, innovative ways. We have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of your screen. You can enlarge the slide window by clicking on the small green icon in the upper right-hand corner of the window, or by hovering your mouse over the lower right-hand corner and dragging the window to the required size. The slides will advance automatically during the event. If you have any technical problems viewing or hearing this presentation, please click on the question mark Help widget in the dock at the bottom of your presentation window. Please note the social media widgets from our sponsor. Concluding the webcast, we ask that you take a brief survey. I would now like to introduce today's speakers. We are pleased to be joined today by Dr. Daniel Stone and Dr. Peng Zhao. Dr. Daniel Stone is a University Academic Fellow in the School of Chemistry at the University of Leeds and holds an Independent Research Fellowship from the Natural Environment Research Council of the UK. His research interests focus on the chemistry of reactive species in atmospheric and combustion chemistry. Prior to his fellowship, Daniel was a postdoctoral researcher at the University of Leeds and the University of Manchester. He obtained his PhD and undergraduate degree in chemistry from University College London. Dr. Peng Zhao is a product manager at Princeton Instruments. Dr. Zhao holds a doctorate in physical chemistry from Texas A&M University and is the author or co-author of more than 20 articles in scientific journals and 7 patents. He has more than 15 years of experience in spectroscopic instruments and chemometrics methods research and development for scientific research and industrial applications. Thank you both for joining us. Peng, please get us started.
Thank you, Kate, and thank you everyone for listening to today's webinar. So I'm going to spend the first 10 to 15 minutes in today's webinar talking about some latest advancements in spectroscopic technologies, particularly spectrograph technology. And I'm going to talk about a special aberration-free design from Princeton Instruments and why it's important for many scientific research. As many of you know, there's a very strong organic bonding between scientific research community and technical development business side. A lot of times there's a driving force behind each other. So we're going to have more webinars like this one we have today. I'm going to share other related technologies like camera technology and share some applications with you. So by saying that, a quick review of what the optical spectrograph system looks like. It typically has a light source, a sampling interface, and a spectrograph which disperses the light into its individual component in terms of wavelength, and a detector which captures the photons, convert it into electronic pulses, and digitize it. And that's how we get a numerical spectral data. The beauty of this is the spectral data has huge amount and rich information of chemical and physical property of the sample you look at. And the carrier of that information is our photons, which means that The measurement can be done in a non-invasive and non-contact fashion. It's a perfect fit for many routine material measurement in the labs, as well as some of the most challenging research that you can imagine. Give you a few examples: atmospheric science research, remote sensing, looking at astronomy, looking at stars light years away, and trying to figure out what chemical composition of those star or planet really is. And in many cases, the optical spectroscopic technology is perhaps the only viable method to do those type of research. A lot of innovation along the way, brighter light source, enhanced sampling method, unique design of spectrograph, and as well as some of the enabling technology and detector technology. So the cornerstone of pretty much all the grating-based spectrograph system out there are based on a so-called CZERNY-TURNER design. It was proposed by two scientists in the early 1930s, and there's really not so much change to the optical design until perhaps a few years ago. There's several product lines being launched by Princeton Instruments that greatly improved the aberration performance, which is intrinsic for CZERNY-TURNER design. About a year and a half ago, we launched a product called Fergie, which is the first aberration-free spectrograph product on the market. So I would like to spend a few slides on what really CZERNY-TURNER design is and why it's been around for so many years. It's a very simple but elegant design: 3 key optics, a collimation mirror, a grating, could be a fixed or rotating grating, and a focusing mirror. Depending on how you detect a signal, you can put a axis slit with single element detector. This configuration is also called monochromator, and which is still widely used in many commercial UV systems that you can find in many labs. The other way to capture a spectrum is using a 2D array detector, and it's also called a spectrograph. So instead of marrying the signal at one wavelength at a time, we can capture the entire spectrum in one exposure. The advantage of CZERNY-TURNER, as you can see here, the design is really simple and elegant. Most of the optical components here are very easy to manufacture, which leads to very low cost of the system, and has pretty decent on-axis performance. The downside is once people start to use the two-dimensional array detector, then now we're not only dealing with the on-axis mode, we also have to be very careful about the off-axis performance. And aberration is some major effect that we have to be very careful how we're dealing with them. So before I get into the aberration, what it is, how it's impacted the performance of the system, let's take a quick look at what an ideal system should look like. We use a point spread function to measure the performance. It's basically an instrument response function of a point source. For ideal system, the point spread function is an identity function, which means that the image is 100% photocopy of the object. It's not going to happen in real world. As many of you know, when light passes through a finite aperture, it's always going to generate a diffraction pattern. So the next perfect system in line is called a diffraction-limited spectrograph, which means that imaging is going to get a little blurred because of this diffraction. And once we add aberration in there, there's 3 major aberrations: spherical aberration, coma, and astigmatism. It's not a new term, probably to many of you, if you're familiar with photography. A lot of time you spend more money on the lens than the camera body because of the design, the complexity of the lens is trying to do an aberration correction. So you have uniformly clear, sharp image at the center of your photon of the picture you take, as well as that corner of the picture. So it's a lot easier to explain with real data. So here is a spectral imaging data of 14 core fiber bundle, vertically aligned, using a CZERNY-TURNER spectrograph. So just want to remind you, for an ideal system, every data point, every point here should look identical. But in reality, if we're only a few steps from the center, we start to see aberration effect, comma, spherical. If we move further from the center, the aberration effect becomes more and more obvious. What's the impact of that on the spectral data? So if we're using a pinhole slit here, using a CZERNY-TURNER spectrograph, looking at an atomic emission lamp, keep in mind every line here are atomic emissions, so it should be extremely sharp and symmetric. But in reality, if we look at a different cross-section across a peak further away from the center, you will notice that the intensity are different, the peaks of location are different, and the peak shape are also slightly different. That's all because of the aberration effect, and that sometimes can be detrimental to particular research. And if we go back to the fiber bundle data here, we can make some compromise here. When we're dealing with the two-dimensional array, we can bring it differently. If we only look at the center, as shown in picture 1 and 2, we can maintain the resolution, but we have to throw out a lot of photons that outside this region. We can also bring it vertically to capture as much photon as we can, but the resolution are hurting here. If we look at another piece of data here using a white broad light source, the aberration effect is also pretty obvious. In this case, there's crosstalk between different spectroscopic channels. As you can imagine, if you want to do hyperspectral imaging measurement, for example, this can destroy the spatial information. So aberration can be corrected. In this case, you can carefully pick a pair of negative and positive aberration optics, and they can balance out each other and give an aberration-free configuration. But keep in mind, it only works at one grading angle. So if the grading is moved, the system is no longer aberration-free. And it's pretty clear in this piece of data here. If you're close to the aberration-corrected angle, the data looks sharp and nice, but once the grading moves away from that optimal point, it's no longer as nice and as sharp. So a quick summary here. Their aberration correction method used by people out there in the commercial system on the market by using toroidal mirrors, concave gradings. There's also can be done with software in algorithm. If we know the point spread function across the entire wavelength range and at every location on the 2D detector focal plane, we can do some deconvolution method and to reconstruct the diffraction-free image. But there's limitations. As I mentioned earlier, typically it only works for a limited spectral range and the grading angles. And it's very hard actually to come out with a form of a point spread function that can cover the entire wavelength range. So what we did in Fergie, the first aberration-free spectrograph, we use a lot of computer-aided design using optical software. We have constructed a very complex merit function to optimize the entire optical train to make it aberration-free, and we have couple of constraints we placed in there. So the first one is use as the minimum number of reflection surface as we can. So every reflection surface can cause some loss there, and it adds up pretty quickly. The second is we want to make sure that the designed optimized optics can be manufactured. So we use two sets of diffraction limited and astigmatic objectives to produce no aberration. This is why the system is not sensitive to grading angles. This is why we can make it work, make it aberration-free at all different grading angles to cover all wavelength range. So this is data taken by using 50 core fiber bundle vertical aligned entrance slit, and you can see clearly that it's as close as you can get to an ideal diffraction limited system. The image of every core fiber bundle core looks identical on this data. And if we look at the spectral data coming out of the previous slide, it's sharp, symmetric, and it looks uniform at low grading angle as well as very high grading angles. So a quick conclusion here, there's a lot of performance degradation because of the aberration. And the only way to do it is the best way to do it also is to design the optics carefully and to trying to compensate those aberrations as much as you can. And why we do that, today I only talked about spectrograph technology, but there's camera technology, light source, sampling, and algorithm. Everything that we're trying to do here is trying to improve signal-noise ratio of the data. There's a lot of constraints, and work around a lot of these constraints is a pretty big challenge. Swab, size and weight, price, dynamic processes, and signal itself are all have different significance, depends on the application and research you wanted to do. So my last slide will be giving an example using the ozone depletion. It's one of the best examples of how human activities actually can have a huge impact on the pretty fragile nature environment around us. And you can find the mechanism nowadays from pretty much any atmospheric chemistry textbook. How by introducing a chlorine atom, the natural balance between ozone and oxygen are shifted greatly towards the oxygen side. And that explains the ozone hole generation, and that's actually lead to a Nobel Prize laureate in 1995. It's really a great combination between lab measurement, field measurement, and modeling. And optical spectroscopic technology played a vital role in this research. It's extremely challenging, and a lot of contribution. You need the best performance in this type of research. And there's still a lot of unresolved problems that Professor Daniel Stone and his colleagues are trying to resolve in stratosphere as well as troposphere. So by saying that, I'm going to pass the presentation to Dr. Daniel Stone.
Okay, thank you.
All yours, Daniel.
Thank you. So I'm going to talk a little bit about some of the work that we've been doing in Leeds, looking at some atmospheric chemistry using a range of spectroscopic techniques. So just before I start, a little bit of background information. So I'm based in the School of Chemistry at the University of Leeds. If you're not sure exactly where Leeds is, then if you look at the UK, we're kind of right in the centre where the red circle is showing you. So the map is showing NO2 concentrations across the UK. So you can see we're in a reasonably polluted region of the UK in the centre there. So the group in Leeds, we've got quite wide interests in atmospheric chemistry and composition and combustion chemistry. So we'll be talking today primarily about the atmospheric chemistry, and this really encompasses experimental work, field work, and atmospheric modelling. And today I'll be looking at some of the experimental work that we've been doing. So poor air quality costs the UK in excess of £20 billion per year. There's large social impacts and health impacts as a result of this. And really, air quality is determined by atmospheric composition. and this is controlled by a combination of emissions and chemistry. So if we want to be able to predict air quality into the future or design policies to address air quality issues, then we really need a fundamental understanding of the atmospheric chemistry that's occurring. So for most species emitted into the atmosphere, they're removed from the gas phase by oxidation reactions. So these reactions initiate complex reaction cascades, producing a number of other species which are potentially harmful in their own right. So one group of species that have been predicted to play a role in the atmosphere for a long time are Kriege intermediates. So they're produced in the atmosphere when ozone reacts with an unsaturated volatile organic compound. So we have an example here of ozone adding to a carbon-carbon double bond. This forms a primary ozonide, and a primary ozonide rapidly decomposes to form a carbonyl compound and an excited Kriege intermediate, so the species on the right there. So the excited Kriege intermediate can either decompose to produce radicals such as OH and HO2, which are also key atmospheric species, or it can undergo collisional stabilization to produce a stabilized Kriege intermediate, so a Kriege intermediate in its ground vibrational state. So it's the chemistry of this species that we're really interested in at the moment, and we can just look briefly at where Kriege intermediates are produced in the atmosphere. So we've got a previous modeling study here that shows the production rate across the globe, and so you see high production rates over areas with tropical forest emissions, so lots of carbon, unsaturated carbon-containing compounds there, but also relatively high emissions and production rates over urban regions coming from vehicle exhausts. So although we think the Kriege intermediate is important in the atmosphere and in controlling composition and air quality, the reaction kinetics of their reactions are highly uncertain. So they've historically been derived from chamber experiments involving ozonolysis reactions, so by producing the Kriege intermediate, using the chemistry that I've just shown. But these are quite complex reaction mechanisms, and the information about the reactive Kriege intermediates are often derived from observations of stable species. There's often multiple routes to production of these species, and so extracting information about the Kriege intermediate itself becomes quite challenging. So ideally what we need to do is to be able to prepare these species in situ and couple that with some rapid and sensitive monitoring. So in 2012 there were some direct measurements of Kriege intermediates by a group in the US, and they showed that instead of using these ozone plus VOC reactions to produce the Kriege intermediate, in the lab we can use diiodomethane. So we can photolyze diiodomethane in a flash photolysis experiment, and we produce an intermediate radical which we can react with oxygen, and we can produce the simplest Kriege intermediate, CH2OO, shown in red there. So what these direct measurements showed is that actually these species are far more reactive than we previously expected. So under the conditions of the experiments, the rate coefficients for reactions with SO2 and NO2 were more than 1,000 times faster than we'd expected on the basis of the previous measurements. And so this has implications for atmospheric sulfate and nitrate chemistry. But the experiments were performed at a single low pressure and a single temperature. So we've been doing some experiments in Leeds to kind of complement these studies and try and extend the pressure range and look at a range of conditions and Kriege intermediates. So the first experiments we did were using laser-induced fluorescence spectroscopy. So we were using the same flash photolysis technique using diiodomethane in excess oxygen to produce the Kriege intermediate, and then we used laser-induced fluorescence to monitor the production of formaldehyde from the reactions of the Kriege intermediate. So we have a reaction cell through which we direct a photolysis laser to create the species, and then at some time after production of the Kriege, we fire an excimer pump dye laser, which excites the formaldehyde being produced in the system, and we monitor the fluorescence from the formaldehyde species. So this is a plot showing the formaldehyde fluorescent signal as a function of time. So we initiate the chemistry at time 0, and then we see what looks like a bi-exponential growth of formaldehyde in the system. So the fast initial growth we're seeing in the system seems to be coming from the Kriege plus SO2 reaction, but we also have a slower production that's coming from some secondary chemistry in the system involving a peroxy radical that's also formed when you photolyze diiodomethane in the presence of oxygen. So we have two sources of formaldehyde in the system, but we're able to obtain some kinetics about the Kriege plus SO2 reaction and the yields of the Kriege intermediate and the peroxy radical from this CH2I plus O2 reaction. And we can do this over a range of pressures. But there are some disadvantages to using fluorescence experiments. So they were useful for looking at the simplest Kriege intermediate in some of these reactions with SO2 and NO2. But there are indications that there's other chemistry going on. And of course, we are limited to observing species that fluoresce in the system. So this really limits the applicability to the simplest Kriege intermediate. But there are larger Kriege intermediates involving more carbon atoms that are of atmospheric interest. So we want to explore other techniques to look at some of this chemistry. So one of the techniques we've been looking at is developing some time-resolved infrared spectroscopy. And so we're using some mid-infrared quantum cascade lasers to do this. So I don't want to talk about this aspect of the work in too much detail, but we're currently using this to look at the production of sulfur trioxide, SO3, in these experiments. So this is one way we can do this, but this experiment is still in development at the moment. And the other experiment that we're developing at the moment is the time-resolved UV spectroscopy. So since the 2012 experiment showing this direct method for producing Kriege intermediates in the lab, several groups have shown that Kriege intermediates have quite large UV absorption cross-sections. So for comparison, the maximum cross-section for the Kriege intermediate is of a similar order of magnitude to ozone. So we have some data here showing cross-sections as a function of wavelength that we've been measuring in leads in the last year or so. And these compare quite favorably with some of the other experiments that have been reported in the literature, so particularly with the results of Ting et al. Shown in green here, and the results by Foreman et al. Shown in orange here. So UV absorption spectroscopy is a promising tool for looking at Kriege intermediates, and it also provides potential for monitoring of some of the other species that are in the system that the laser-induced fluorescence experiments indicated was occurring. So looking at the spectra for the precursor diiodomethane shown in green, here we should also be able to see any changes to the diiodomethane concentration using UV absorption spectroscopy. We can monitor IO radicals, which are shown here in the purple. If we shift to lower wavelengths, we'd also be able to see some of the peroxy radical chemistry that's occurring in the system. And if we shift to higher wavelengths, any potential production of I2 or OIO in the system. And this experiment will also be applicable to some of the larger Kriege intermediates, which has been shown recently that you can produce by flash photolysis of similar diiodo precursors. So the flash photolysis experiment coupled with time-resolved UV is a promising tool for us to look at Kriege reaction kinetics. So just wanted to have a look in a bit more detail at our experiment. So we have a reaction cell. So our reaction cell is about 2 inches in diameter and about 1.5 meters long. And we have a constant flow of well-mixed precursor gases through the reaction cell. We use an excimer photolysis laser that we direct down the center of the cell. So we have a brief pulse of UV light at 248 nanometers to initiate the chemistry that's occurring in the reaction cell. And then we use a laser-driven light source which provides output from about 200 nanometers up to about 800 nanometers that we can use in the system. And we multipass this light through the reaction cell. And so we get an increased path length in our experiment. So we have a path length of about 11 meters when you consider the overlap between our probe beam and the photolysis laser. So finally, we detect this multipass light on a detector. So we have wavelength resolved probe light intensity measured before, during, and after the reaction. So, as I'm sure you've probably guessed, the detector that we're using is the Princeton Instruments Fergie imaging spectrometer. So it's a spectrograph combined with, in our case, a UV-enhanced charge-coupled device detector. So we're fiber coupling our probe light to the Fergie instrument, and the spectrograph gives us wavelength resolution. We're using a diffraction grating that gives us about a 540 nanometer spectral range. And we image this onto the CCD detector, which is an array of light-sensitive pixels. So the CCD detector can operate in several modes, so we can use what's called a full-frame mode, and we can use this to monitor the absorbance of stable species in the system. So we can monitor the precursor composition that we're using in the system using the full-frame mode, or if we're looking at transient species, we can use the spectrokinetics mode in our flash photolysis experiment. So when we use the spectrokinetics mode, we're imaging the output from the spectrograph across an illuminated region on the CCD. So in our case, the illuminated region is 10 rows by the full column width, with the remainder of the CCD used as a storage region. So if we imagine the CCD as being this 2D array of light-sensitive pixels, then if we have just here the top row of the CCD as being the illuminated region, and then the shaded region is our storage region, then if we image the spectrograph output across that illuminated region, and then we can rapidly shift that intensity, or the charge that's generated by that intensity on the CCD, down the CCD into the storage region row by row. So we can get a rapid row by row shifting into the storage region, and this gives us our time resolution in the experiment. And so using the spectrograph coupled with the CCD detector, we can get spectrally resolved intensities recorded on rapid timescales. So the analysis of our reaction, we're using the Beer-Lambert law. So we're measuring intensities, as I say, before, during, and after the reaction. So we have the intensity at a given wavelength before photolysis, and we can compare this to the intensity at that wavelength at a time after photolysis. So if we take the natural log of that ratio, that gives us the absorbance at that particular wavelength and time. And we can then, using the Beer-Lambert law, we can say that's equal to the sum of the absorption cross-sections of species I at that wavelength, multiplied by the concentration of that species at that particular time, multiplied by the path length. And so we can use this analysis to go from our intensities to calculate the absorbance, and then determine the exact time-dependent composition of our reaction mixture. So we can determine the concentrations of each species in the absorbing region as a function of time. And it's that we need in order to determine the kinetics of the reaction. So if we're looking now in terms of the intensity that we measure, so the plot shown here is the intensity at a particular wavelength, so in this case at 340 nanometers. So this is the peak of the Kriege absorption spectrum. So this is plotted against the frame number, which is essentially the row number on the CCD, so it's equivalent to a time point during the course of the reaction. And so what we see at the start is that the intensity is reasonably stable, so this is just monitoring the intensity of our probe light. And then at some time, just after frame number 90, we fire the photolysis laser, and we see a brief spike in the intensity because of some scatter from the laser light that we don't quite filter out. And then we see a decrease in the intensity as we're producing the absorbing species. And then as that species reacts, we see the intensity come back to the baseline level. So that's looking at the data, kind of a slice through the time dependence of the intensity. But of course we have a three-dimensional data set from this experiment. And so what we actually have is the absorbance as a function of the time and the wavelength. So shown at the back of the plot there with the highest absorbance in the center is time 0, so when we initially create the Kriege intermediate in the experiment. And then we see that peak decay as a function of time as the Kriege intermediate is reacting in the experiment. On the high wavelength side, on the far right of that plot, is where we see the IO signal. So we can distinguish between the Kriege and the IO absorption quite nicely in this experiment, and monitor the concentrations of both as a result. And so if we now look at a single time point in the experiment, so looking at the full spectrum as a function of time, a single time point, then we see the absorbance shown here in black. So again, we have the IO signal at around 400 to 450 nanometers, and the Kriege signal peaking at about 340, 350 nanometers. And we can fit the Beer-Lambert law to this to extract the contributions from each species present. And so we have here the green part shows us the depletion in the diodomethane precursor, the concentrations going down as we're photolysing. And we see the Kriege intermediate contribution shown in blue and the IO in purple. And then the total fit to the data shown in red there. So we do this for each time point in the experiment and fit to the spectra. And what we end up with is a concentration versus time, or in this case shown here, a concentration versus frame number throughout the experiment. So again, showing this rapid increase in concentration on the photolysis event, followed by the decay as the chemistry is occurring in the system. The concentrations we're using in this experiment are on the order of about 10 to the 11 to 10 to the 12 molecules per centimeter cubed. And anyone who's not familiar with these units of concentration, that's in the orders of parts per billion. So the signal to noise we can achieve in these experiments from the combination of the camera sensitivity, the multipass experiment, and the data extraction using the full spectrum to determine the concentration allows us to work at these low concentrations. So once we have this concentration versus time plot, we can use that to determine the kinetics in the experiment. The first experiment we started to look at was the reaction of the Kriege intermediate with SO2, just to kind of characterize the experimental setup and show that we had everything working properly. So our experiments are performed under pseudo first order conditions, so our SO2 concentration is in large excess of the Kriege intermediate concentration. And so what this means, if we're looking at the rate of decay of the Kriege intermediate, this is given by some rate coefficient K multiplied by the product of the Kriege intermediate and SO2 concentrations. If the SO2 concentration is much larger than that of the Kriege intermediate, then the SO2 concentration doesn't show much of a change relative to the Kriege. So we can assume that the SO2 concentration is constant throughout the reaction. And so we can then define a pseudo first order rate coefficient K prime from the system. And so we fit our observed data, so shown here is our Kriege signal as a function of time in the experiment, and we can fit to our kinetic decay shown in red here, and we use this to give us our pseudo first order rate coefficient K prime. And so you can see the fit to the data here is quite good. And so we repeat this for a number of SO2 concentrations, and we obtain a number of different K prime values for each SO2 concentration. And this should give us a straight line with a gradient that's equal to the bimolecular rate coefficient that we're interested in. So that's shown by the red line here. So the fit to this gives us a number that's in good agreement with those coming out of other recent studies and with our previous study using the laser-induced fluorescence experiment. So this gives us confidence that the experiment is kind of set up well and is working. And so some of the other systems we've been looking at more recently is the reaction of the Kriege intermediate with methanol in the vapor phase. So there is some potential atmospheric significance to this reaction. There's relatively high concentrations of alcohols in forested regions coming from biogenic emissions, and we saw previously that these are the regions where the Kriege intermediate concentrations are quite high. There's certainly importance in atmospheric simulation chambers where concentrations of the organic species are typically higher than we would encounter in the atmosphere. And if we want to fully understand what's occurring in these simulation chambers, then we need a good understanding of the kinetics of the individual processes occurring. But also what we're interested in is providing some information from a similar system to understand the reaction of the Kriege intermediate with water and the water dimer in the atmosphere. So it's expected that the reaction of the Kriege intermediate, the C1 Kriege intermediate, this CH2OO, with water vapor and with water vapor dimer is a dominant loss process for Kriege intermediates in the atmosphere. And so we're interested in looking at methanol as a similar reactant as water to see if we can understand a little bit more about this reaction. And so again, we have our experiments where we monitor the concentration of the Kriege intermediate as a function of time during the experiment. And these data shown here are the same data that I showed previously in terms of the frame number of the experiment, now given here in terms of the actual time since photolysis with the fit to the data. And so again, we repeat this as a function of the methanol concentration, and we obtain a bimolecular plot. And you remember in the case of SO2, we see a very linear relationship, which is what we expect for these reactions. But the data with methanol seems to show a quadratic dependence. So this is indicating a potential reaction with the methanol dimer or production of a Kriege methanol complex, which then undergoes a subsequent reaction with a second methanol molecule. So this seems to be quite similar to the reaction with water, and we're currently doing some more experiments and trying to look at this at lower temperatures to clarify the role of complex formation in these processes. And I just wanted to have a brief look at the other system we're currently looking at in these experiments, which is the reaction of the Kriege intermediate with ozone. So again, ozone itself is a constituent of the atmosphere. There is a potential role for this in the atmosphere. But we're also now developing experiments to monitor Kriege intermediates directly from ozonolysis of unsaturated VOCs in atmospheric chambers. So instead of using the flash photolysis experiment with diiodomethane, we want to look in ozonolysis reactions to use a more typical atmospheric source for these. So the experiments that we've been doing indicate that we should have the sensitivity that we need in order to do this that wasn't possible before we had the information about the UV spectrum. So we're currently investigating the role of the Kriege intermediate plus ozone reaction. At the moment, still using the flash photolysis technique to do this. So we're using the diiodomethane precursor still to produce our Kriege intermediate. And we see our total absorbance here as a function of wavelength. So again, we're seeing the peak from the Kriege intermediate at about 340 to 350 nanometers, and we see the IO signal at these sharp peaks on the right-hand side of the spectrum at around 420 nanometers. And again, we can fit all our known absorbing species to these absorbance spectra to determine the concentrations of each species that are present in the system. So shown here is the fit to each species in the system. And what we're seeing at the moment is, in the presence of ozone, there's significant secondary chemistry involving iodine and IO. And so we know that iodine atoms are produced when we photolize diiodomethane and create the Kriege intermediate. In the presence of ozone, these iodine atoms react with the ozone and produce more IO radicals than we have in the absence of IO. So we see quite high concentrations of IO in this system, but in these experiments we are able to monitor the time dependence of those concentrations. And so what we're doing at the moment is a lot of data analysis to try and extract the kinetics of the ozone reaction and the IO reaction and improve the sensitivity to those. But as I say, ultimately what we're looking to do is to enable direct detection in ozonolysis reactions. And so I'd just like to conclude the talk just by going back over some of the background. Why we're interested in this area is really to understand atmospheric composition and how it controls air quality and climate. In order to do this, we need to understand the chemistry and reaction kinetics of the reactive trace species that are important in the atmosphere. The species that we're looking at the moment is the Kriege intermediate, which is produced by unsaturated VOCs reacting with ozone. We're using flash photolysis experiments to determine the reaction kinetics with the time-resolved broadband UV spectroscopy using the Fergie system, and we've been able to look at the Kriege reactions with SO2, and we've got some experiments in progress to look at the reactions with methanol and with ozone. Our future work will start to look at some of the larger Kriege intermediates, and we'll start some atmospheric modeling to look at the impacts of all these reactions once we have some more concrete kinetic data. And in the next few months, we should be in a position to extend the UV experiments to provide some direct measurements of Kriege intermediates in ozonolysis reactions. So finally, I'd like some acknowledgements to my students, Zara and Charlotte, to my postdoc, Lavinia, some of the master's students that have previously worked with me, and Paul and Mark Nurk for funding, and thank you for your attention. And with that, I will pass back to Kate.
Okay, thank you, Daniel. And thank you, Hong, for such informative presentations. Before we get started on the question and answer session, I would like to remind our audience how to submit questions. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of the presentation window. And our first question is, it isn't clear to me in the presentation, can you tell me whether or not Fergie is just a spectrograph, or does it have a camera as well?
Okay, I can take this one. Fergie is actually integrated system with a spectrograph as well as a deep-cooled CCD detector.
Okay, thank you. And our next question is, most data you showed were taken with either atomic lamp and white light source. I am assuming you can do absorption and perhaps emission measurements. What other spectroscopic measurement can you do with the Fergie system? Can you measure libs?
Yes, the reason that I only showed atomic emission lines and a wide broad light source is it's the best embodiment of the aberration-free feature in the system. The Fergie spectrograph system itself is a general purpose system. We have customers using it for Raman measurement, for example. We have customers using it coupled to a microscope to do hyperspectral imaging measurement. And the aberration-free feature is a big advantage when you actually measuring hyperspectral data cube. For LEAPS, it's somewhat similar to what Dr. Daniel Stone is doing, using a pulsed laser, and it's absolutely doable with the spectroconnected mode or just simply frame transfer mode. The timing can be a little tricky, but we do have customers using the system for LEAPS measurement as well.
Thank you. And our next question is, can you explain a little bit more how Fergie is coupled to your multipass cell? Are you using a delay generator to synchronize everything?
Okay, so I think this is one for me. So we are using a delay generator to synchronize. So we couple the light into the spectrograph using a fiber optic. But to control the timings, there's the option of either using the Fergie itself to generate the TTL pulses to control external outputs, but we are using an external delay generator, and so we use the delay generator to define the time zero of the experiment, and so we have the TTL pulse then that initiates the camera, and then at some time delay later, the delay generator is firing the pulse to fire the photolysis laser. And so we have this repeating on a cycle, so we can fire the photolysis laser every 4 to 5 seconds, because actually what holds us up in the experiment in that respect is that we have to refresh the gas in the reaction cell between every photolysis shot. So yes, we use a delay generator to control those timings.
Okay, thank you, Dan. And our next question is, I think this is for you as well. How do you decide to study certain species and its reaction, for example, Kriege, given that there are perhaps hundreds of chemicals that can be found in the atmosphere?
It's a good question. So there's certainly much more than hundreds of different potential chemicals. Estimates of organic compounds on the order of tens of thousands. And so really this comes from the links between groups who are looking at field measurements, doing modeling work to explain those measurements and the laboratory work. And so often what happens is that it's the connection between those three areas that drive what we're looking at. And so, for example, if there are field measurements that go to a certain location and have some observations that aren't explained by the modeling that's being done alongside them, then it indicates that there's something wrong with the inputs to the model. And so that gives us an idea of which areas we want to look at in the lab to kind of improve the modeling capability to understand the field measurements. So, for example, in recent years there's been some measurements of SO2 and sulfuric acid in the atmosphere, and previously it was thought that the only way in the gas phase to oxidize SO2 in the atmosphere was through reaction with the OH radical. And experiments were being done in which the OH radical was being scrubbed from the system, so being removed completely. And the field measurements were still showing significant oxidation of SO2 to sulfuric acid, indicating that there was some other oxidant present. And the location that they were in had large emissions of biogenic species, so lots of unsaturated VOCs coming from trees. And this unknown oxidant of SO2 was correlating with emission rates of these unsaturated compounds from the trees. And so it indicated certainly that there was something in the chemistry of unsaturated VOCs that we should be looking at. And it's been predicted for a long time for some theory studies that these Krieg intermediates could potentially play a role in the atmosphere. And so that's really where the kind of drive has come from to look at these Krieg intermediate reactions in more detail.
Okay, thank you. Our next question is, what is the time resolution of your setup?
Okay, go ahead, Dan. Sorry.
So yeah, I guess this is probably something for us both to comment on. So in our particular reactions, we're looking on timescales of perhaps hundreds of microseconds, and so depending exactly which reaction, how fast the reaction is, we want to vary that a little. But for us, typically hundreds of microseconds. But I think Peng can probably say a little bit more about the time resolution that's available with the system.
Yes, Dan. The limit is basically how fast you can transfer a single in spectrokinetic mode. How fast we can transfer a single line of pixel to the readout port. So the theoretical limit is in around 5 to 6 microseconds, but in reality, I would say probably 10 microseconds is a comfortable time resolution we can achieve with the CCD detector we used.
Okay, thank you. Our next question is, this is for Daniel. Why do you use a diffraction grating that gives approximately 540 nanometer coverage when you're only looking at 100 to 150 nanometer range between 300 and 450 nanometers?
So the range we're looking at between 300 and 450 contains all the contributions from the species that we're particularly interested in. So the contribution from the precursor, the Krieg intermediate itself, and any IO radicals that are formed in the system. The larger coverage, it gives us the potential to look for any I2 or OIO that's formed in the system. But primarily the reason we do this is because our probe light has some fluctuation in the intensity output. And so we can use the intensity at higher wavelengths where there's no absorption occurring in the system to kind of track that fluctuation in intensity and do some normalization for it.
Okay, thank you very much. Unfortunately, we are now out of time. I would like to thank the audience for attending and for participating in today's event. I would also like to thank our sponsor, Princeton Instruments, for making today's educational webcast possible. You will receive an email from Spectroscopy alerting you when this webcast will be available for replay. We invite you to forward that announcement to your colleagues who may have missed today's live event. We look forward to seeing you all next time. Goodbye.